sucks them up. Polarization. It's defined as the orientation of the electric or electrostatic field with respect to the Earth. So there is no polarization in free space. When it's on the Earth, depending on whether it's a horizontal or a vertical antenna, will basically give you horizontal or vertical polarization. As long as it's line of sight. If you got propagation and it's bouncing off the ionosphere or possibly even other buildings, the polarization can become elliptical because of some phase shifts.
Was it space is omni?
Huh?
Space would be omnidirectional.
Yeah. Well,
Nothing
if it's a dipole in outer space, it's still going to have that donut, but it's going to be perfectly symmetrical because there's no ground effect or anything. Okay, so for VHF and UHF, for line of sight things, if you have crossed or differing polarizations, in other words, if you got your handy-talkie and holding it up, I'm vertically polarized. Okay, if he's over there and he's got his that way, horizontally polarized, the signal is just going to be the intersection of those two. It's going to be very, very small. Whereas as you rotate them and they line up, because you've got matching apertures, basically, then you're going to get the maximum amount of signal. In long distance work, and I don't know how you do long distance on UHF, but I don't.
Horizontal.
Right, but
That's
I mean,
we use sideband on VHF, UHF. Normally,
other than satellites, who do you contact long distance on UHF?
there's the
Because it's line of sight.
They use propagation
For UHF?
On 2 meters a lot. 4 meters, 2 meters.
Well, that's
people run single sideband.
Yeah.
And they use it horizontally.
Right.
And you get some skipping effect.
Yeah.
And it goes with a lot of it with temperature and also with the sun, evening and morning. They call that solar phase or whatever it is.
Yeah. I think there's a chart showing a little bit of that later.
Yeah.
And basically that's because of it. When you get refraction, you're becoming elliptically polarized, basically circularly polarized, except it's not perfectly circular, so it's elliptical because circle is a special case of an ellipse. So it really wouldn't matter, and it's typically easier to do, like with the beam antenna, horizontal than vertical, which comes up a little later as a question too. And for repeater handheld, normally you want to stay vertical. So if you really having trouble talking to somebody, you want to try to keep both antennas up or sideways, but they need to be the same. And typically a repeater is always going to be vertical. Okay, here's actually showing the difference between elliptical or circularly polarized and your normal linear, where you got a horizontal and you got a vertical. Now you can transmit both with a crossed antenna and do horizontal and vertical signals. And sometimes they do that for satellite reception because it's not only possibly elliptical, but it's rotating, the Faraday rotation. What property of a radio wave defines its polarization?
Okay.
Yep. Electric field with respect to ground. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization?
Bravo.
What antenna polarization is normally used for long distance CW and SSB contacts on VHF and UHF bands?
So,
And it's normally because they're doing it with beam antennas, and big beam antennas are, although they wouldn't be that big at VHF, UHF. So I don't know why it would be a problem doing them vertical.
that would be similar to the old TV antennas, right?
Yeah, I mean, those typically are Yagis or log periodics. And you always see them horizontal, but on those,
TV signals are still transmitted with vertical. After a certain distance, they end up being scattered and end up horizontal. Works just as well.
okay, VHF are most often line of sight. There's some modes that can allow you to communicate long distances around the world and more. I don't know if you can do 2 trips. I guess if you had enough power and the right propagation, you could. In fact, I don't know that it comes up in the tech, but in the general or extra, they talk about problem of short path and long path, where you can be talking to somebody 2,000 miles away, but they're also getting your signal all the way around the world, and they obviously come different
Times.
delays. Okay. VHF may bounce off the E layer. And in the chart down here, they define the different ionization layers of the ionosphere as the D layer, which is the lowest one. It's basically an absorption layer because it's got the most oxygen molecules. This is the lowest one. It's the most dense. So it tends to absorb frequencies and it disappears at night, which is why those same frequencies work at night and they don't work very well in the daytime. Then you have the E layer, which will allow some sporadic propagation where it hits the E layer and it scatters. Some of it comes back, some of it comes down, some of it goes up. So it's not very reliable. That's why they call it sporadic E. But you can get over the horizon with it on these upper bands. And the 10 meter is best in the daytime with high sunspot activity. And all these are affected by solar activity, the sunspots and how much radiation is coming out, flares, all that stuff.
You have to go in their light system to get good.
We have some charts on that.
Huh?
We have some charts on that coming up.
Oh, I didn't know that.
Isn't that because we have more ionization in the atmosphere?
Yep.
Sunspot activity being higher.
Yes,
Yes.
yes. But it can also blanket everything and
Over.
send it down the tubes, which happened here just a few days ago, right? Yeah, a week or so. Okay. Oh, I added this and I didn't erase the other stuff. Just look at the picture. It's showing skywave propagation and different angles of what do they call it? Not angle of attack.
Reflection.
Launch angle, I guess. Anyway, depending on your antenna and the pattern, it will have a maximum density, power density at some particular angle relative to the Earth. And usually it's optimized that when the antenna is half a wavelength high. When as it gets lower, the angle tends to go up. In fact, when you get all the way down, then you get into the NVIS, where you're basically shooting straight up, so you can do short range communications. When you get to half a wavelength, then that's about as low as it's going to get. When you get higher than that, it doesn't get much lower, but you start getting additional lobes going up, so you're losing power. So it's less, even though it might lower a little bit, it's not as strong as it was. So the optimum is half a wavelength. Right?
That's where I understand it.
In this, yeah, which you may not be able to read, talking about a dipole at half wavelength. And they're bouncing off the F layer, which are the highest layer, which is split into two during the daytime, the F1 and the F2. At night, it condenses into the F layer. So basically at night, you have an F layer and a E layer. Okay, so auroral backscatter, meteor scatter, tropospheric scatter, all kinds of scatters, and ducting. So auroral backscatter is you bounce a signal off of the Earth's aurora, the northern or southern borealis, which they call aurora borealis or aurora australis. And it's due to the magnetic field of the Earth and the solar wind hitting it, and somehow, ionizes all that stuff and makes a big donut. And you can see it from, I was told, I've never seen it in person. Michigan people can see it.
I've heard of it down as far as Pennsylvania,
Really?
but I've never seen one.
I've never seen it, but I think,
You can't see it
Iceland,
through.
Greenland, when you were stationed in Canada, were you able to see it there?
Oh, yeah, I saw it in Alaska, I saw it in Canada, I saw it in Greenland,
Is it pretty?
green.
Well, that's the way this picture coming up is. Okay.
Smells the Jacksonville,
A solar flare can cause the auroral zone to increase in density and expand, making it capable of scattering without significant absorption. I'm guessing that under normal conditions, it may absorb more than it reflects, but I really don't know. It's too far away.
That's right.
I can't imagine you can rely on this.
Yeah, right. That's the thing coming up next. It's distorted, can vary. It's not reliable. Like all these we're talking about here, they're basically sporadic things. Okay, here's a picture of the northern and southern auroras. You can see much more intensity over here on one side, and same thing on the southern one. I don't know why that is, but my trust.
Like you can't see it.
That's probably at the angle of the.
Oh, actually, I didn't. Yeah, you're right. It's brighter over here in the
In the dark. area.
time. Yeah,
It's there.
which
but
probably has something to do with the day-night stuff on the other things, like the layers going away.
Mhm.
Okay. Meteor scatter. Now, I've been told that, and I think there's some NASA club members that have done this and bounced off of meteor showers. They leave an ion trail behind them. So if you're at the right place at the right time and the right angle, you can bounce a signal off of it, and maybe somebody will pick it up. But again, it's scatter. Okay, so only a portion of it is going to get somewhere and it's not very reliable. Certainly not something you could depend on happening. Right. And it's, best on this 6 meter band. It turns out 6 and 10 meters are good for lots of things.
I don't use them.
And we have tropospheric scatter. Okay. The troposphere is below the ionosphere. And it can also scatter as opposed to refract waves. And again, it's sporadic. So it's just it may happen, it may not. And there's little things showing where actually most of your signal is just going straight through. And some of it is being scattered down, some of it's up. So what proportion somebody would actually receive, I don't know. But if this is representative, it's very small. Then there's tropospheric ducting, where in the troposphere, you can have a temperature inversion where you get a warm layer of air above a cold layer of air. And it acts like a duct for radio waves, and will actually propagate along that duct, like microwaves do in waveguides, similar kind of thing, except much lower frequency. And I don't know, have any idea what the relative distances are that you can get? Have you ever done tropospheric ducting?
Never did.
Well, you might have and didn't know it.
I could have, but
Okay, there's just another chart showing the warm air, dry air, and the difference in refraction. So it's going to depend on the critical angle. And I don't know if we get into that later, but critical angle is dependent upon other factors, and that's whatever angle or the highest angle that will refract. It's dependent on frequency and the conditions of the ionosphere, whatever it's refracting off of. So those angles will change. So, and it's just like light bouncing off of a piece of glass. At a certain angle, it'll reflect. Higher than that, it goes straight through.
So you mentioned it earlier that water has something to do with the transmission. So on like a heavy fog day, does that interfere with the radio signals?
Microwave and UHF.
Yeah.
It wouldn't affect HF, right?
not to the same degree.
Oh, yeah.
Very minimal.
Which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, and 2 meter bands from beyond the radio horizon?
I would say you know what you mean.
So we have an A,
I'll pick B just to be different.
a Baker, an Alpha,
A couple of them, D region. And a great line propagation. That's the word I was thinking of before.
oh,
Day and
okay,
night,
yeah, right, gray line. As opposed to the A line.
right.
Well, let's see.
No.
Remember, we talked about sporadic E at the 10, 6, and 2.
So the reason why I didn't think sporadic is because it says most commonly associated.
Yeah.
I was thinking the opposite of the word.
It's kind of a trick question. That way you remember it. If you get that question, I'm sure you get it right.
Mm-hmm.
What is a characteristic of VHF signals received via auroral backscatter?
B. And so am I.
Makes sense.
Distorted and vary in strength. What band is best suited for communicating via meteor scatter?
Big.
Is they call that the magic band?
I don't know what they call it.
I think it's 6, as they call the magic band, 6 or 10. One of them. What type of propagation is responsible for allowing over the horizon VHF, UHF communications to ranges of approximately 300 miles on a regular basis? I don't think I talked about the distance. So what would that be?
Let's say,
I go with ducting.
Because we didn't talk about the other ones.
well,
You
yeah,
just,
yeah,
you
two-
still are going like that.
Yeah, but that didn't say how far.
Oh,
I need to go put that 300 miles in there.
Yeah, because F2 is only during the day.
You
The
get
what?
that a lot.
The F2 is only during the day, right? Because it splits layers.
Well, F1 and 2 are there all, well,
But-
F1 and 2 collapse into F at night. They're not separate. But the tropospheric ducting is down much lower, below the ionosphere.
You also get that when it's sunrise and sunset because you have the two different things. That's ducting down that way.
As you usually listen.
What causes tropospheric ducting? Delta, delta, delta. Precipitation. Rain, snow, ice, fog can absorb microwaves, thereby decreasing the range, absorbing the signal, which means it's not going to go as far. Well, it may go as far, but it'll be a lot less energy in it. It has little or no effect on lower frequencies. They don't define lower frequencies, but I would say most of the HF band, it doesn't have much of an effect. What weather condition might decrease range at microwave frequencies?
See.
What's the effect of fog and rain on signals in the 10 and 6 meter band?
Well.
Should be little effect on. Yeah.
I missed that one the other day when the guy was taking his test. Because 6 meters is VHF.
That's A would be for UHF and microwave.
So
Very edge.
it's kind of okay. Basically, we rely on propagation at HF frequencies to do long distance reliable communications, where all these things we talked about, all the scatters and ducting and things are not very reliable, and they don't get the same kind of distances. Whereas at HF, refractions off the ionosphere, like I said, you can go around the world. I mean, I pick up Australia, New Zealand easily at 50 watts.
And no commercial aviation, they use the HF band when they're like transatlantic, trans-Pacific.
At 20, 15 meters, those, I mean, actually probably see more Asia and New Zealand, Australia around 17, 15. They tend to operate there more, I think.
Aircraft now are usually satellite communications.
Yeah, they still have an HF antenna in them.
I don't know.
They run up the tail stabilizer.
Okay. The ionosphere is created by solar radiation. So it's those energy particles or waves, whatever all that junk is that comes from the sun, because it spits out all kinds of things, X-rays and cosmic rays and
Mhm.
and that can ionize the oxygen atoms in the upper atmosphere. It gets down into the D layer, which is the lower part, but because it has to go through a lot of it is energy is absorbed in making ions in the F layers. But since there's more oxygen at the lower layers, then you get a stronger effect, which is why the D layer, I think, absorbs more signal. It goes anywhere from 50 to 600 miles above the Earth. So the F1 and F2 layers are up there in the 4, 5, 600 mile, and they vary depending on conditions. And they just talk about the three, the D, E, and F, which we talked about, D being the bottom, but it's still above the troposphere. Here's one, and here you see the troposphere way down here, like 12 kilometers and below. And the ionosphere, the E and F layers, and I still have never figured out what this graph sort of shows, but you can see the height where the ionosphere is part of the exosphere and the thermosphere, and they're up in the 600 kilometer plus. This is just another chart showing the same kind of thing. The difference between day and night, where you only have basically the E layer and the F layer at night. This is a prettier one, kind of showing the difference in refraction off of the different layers. And that is a function of frequency. Like this one over here is probably a UHF signal. This is just kind of going straight through. The lower frequency signals are down here and they're getting bent by the lower layers. They may get a little farther, the higher the frequency. I'm showing one here where some of them refracted all the way and some of them don't quite make it. This is another one I found showing the day-night differences in frequencies. So here you've got your 80 meter, 3.5 megahertz is, I guess, doing ground effect.
Yeah.
And then 40 meters, it's refracting off of basically the E layer. Your 10 megahertz, which is 30 meters, is getting up to into the F layers. And then they're showing 30, I guess, and above really not being refracted during the day. I don't think that's entirely true because I was making some 10-meter contacts pretty far away.
These are typical.
And then, of course, at night, things change. Basically, everything's coming off of the F layer. And this is another one showing the difference in 1 megahertz, 20 megahertz, how the distance they go, the hop or skip, whichever you want to call it, changes. I found a lot of these charts, didn't I? Same kind of stuff.
So in theory, if you were to talk to somebody, let's say on a space station, you want a UHF frequency.
Well,
So you didn't
basically, the satellites all use UHF, VHF. And one of the things,
They transmit on
yeah,
one is back in another one.
I don't think it's in the tech. One of the questions that will come up is they use a format of U/V or V/U, which is represent uplink versus downlink. So it may have a UHF uplink and a VHF downlink or vice versa. So that is what the UV means, whether it's up, which one's uplink, which one's downlink, and they transmit on those two bands. Which region of the atmosphere can refract or bend HF and VHF radio waves? Good old ionosphere. What is the characteristic of HF communications compared with communications on VHF and higher frequencies?
There we go, sir. Yeah.
Sunspots. Okay, 6 and 10 meter band propagation supposedly is best when there's many sunspots. And there's things where they keep track of that. You can look at it daily of what the sunspot predictions are and what they actually were. It's an 11-year cycle. We're currently in, I think, year 3.
Yeah, it's going up now. It's getting
Right.
better.
So we'll be peaking here in another couple years. So it is getting better. This is the 25th cycle since they started counting them, because it's been going on for a long time, actually. And the more sunspots, the more radiation reaches the Earth, more ionization, which gives more reflection or refraction, which is why it's better for long distance propagation. And also, it allows you to operate at higher frequencies. It increases the MUF.
The muff.
The MUF, the maximum usable frequency, which is another thing that they predict on these based on the critical angle and propagation conditions. What's the highest frequency you can operate at that will still get refracted? Higher than that, it goes straight through. At least that's the way I understand the MUF. And then there's a LUF, which is the lowest usable frequency. And I don't understand that one, why that works.
I don't, never even heard of it.
The LUF, well, it's on the exam. Not this one, though.
Is that extra?
Well, definitely the extra. I think it shows up on general. I get them confused. When we have a person taking the exam and you do it online, I get to watch them answer. And, we've had a number of them here lately that do all three. They'll take the tech pass, take the general pass, take the extra. And it sort of is a jumble because you go through and you kind of take the test with them.
Mm.
And even though they can't hear or see you, you're, no, not that one. And then sometimes you get them wrong. It's hard to remember all that stuff. Okay. This one, I think, is attempting to show the difference between day and night. We're over here in the Earth's shadow, or the night portion, how the D layer totally disappears, the E layer becomes much thinner, and the F layers combine and collapse and actually, I think, get a little lower. Which probably means that you don't get the same skip distance because the layer's not as high. And the higher it is, the farther you're going to get on that hop.
The lower angle.
Well, and a high, even the same angle, if it's higher, it's going to go farther. And at the daytime, you've got all those layers in effect. So, which of the following bands may provide long distance communications? HF. These are UHF. And obviously all these choices are correct is incorrect. Okay, the ionosphere changes throughout the day, especially at night. It's best on the higher frequency bands, the 10, 15, and 20 during the daytime. Now, it's been my experience that 20 operates about the same 24/7.
It is pretty good all the time. 10 and 15. Right. Seems to drop out when you don't have. It's getting better now. Before
Yeah.
it was a couple of years ago, you couldn't hear anything on 10 meters. Now you're starting to hear it.
Yeah. Yeah, I've been getting a few contacts on 10, pretty far away. Okay, so it's best at the 160, 80, and 40 at night. Whereas 40 during the daytime, because of depending on how much absorption in the D layer, you may not get too much.
It's also very noisy.
Oh yeah. The lower bands tend to be very noisy, especially if you're around power lines and things. They tend to pick up some of that noise.
Or charging stations.
And for some reason, a vertical you would think wouldn't be, but verticals are noisier than horizontals
Really?
at those frequencies. Yeah. I didn't understand that, still
I
don't.
don't understand it either.
But I think I saw an explanation that said most of the man-made noise, like power lines and machinery and stuff, tends to be vertically polarized. Why, I don't know.
You ever drive by Tesla down here?
No. Well, yeah, but
Have your AM radio on? It'll disappear on you.
because of the charging stations.
Yeah, when they're charging down there.
Yeah. Okay, irregular fading. The ionosphere is constantly changing. I mean, its atmosphere, it depends on the ionization, depends on how much solar activity there is at the time. And it's kind of like, think of it as clouds, and it's not a nice smooth surface to bounce off of. It's lumpy. So sometimes, I mean, depending on what part of it you hit, you can't determine the angle that it's going to reflect that or refract that. I suspect it has different densities too. So because of that, you can get kind of a multipath because you can get two different reflections off of the ionosphere, and they may combine or they may subtract from one another when they get to the receiver. This is the big ARL band chart, and it's got a nice map on the back.
Yes.
I'm going to try to get some more of those. I'm almost out. They make me buy those. The other stuff free. Okay, so you just need to kind of get familiar with that. The farther you go, like general and extra, there'll be more questions about these little sections of the bands, which I can't ever remember. That's some of the stuff you just have to memorize for the exam.
Power limits. And they keep changing them too.
Yeah. Okay, what is generally the best time for long distance 10-meter band propagation via the F region?
See? Charlie?
For low sunspot activity?
Oh, those, okay. Hold on. I might have to- Ding, ding, you wanna read the wrong thing.
Yeah, you can cancel two of those.
Mhm.
What is the likely cause of irregular fading of signals propagated by the ionosphere?
D.
Kind of multipath. Polarization. On the HF bands, it isn't nearly as critical as it is on VHF and UHF. Like we showed with the handy talkies, if they're cross polarized, you hardly pick up anything. Where in HF, things tend to get elliptically polarized, whether you want to or not. So it doesn't really make much difference, especially if you got propagation where it's being refracted. It's definitely not going to come back the way it was sent. Which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized?
B.
Okay. Coffee break, pee break, and then we'll see if we can contact somebody. Oh, I told them around 11. That's not too bad. 11:10. Even though we didn't hurry. There's coffee.
I got water.
There's snacks.
No,
I'm
I
gonna
got
have,
enough fat.
huh?
I got enough fat. I don't need any extra.
Yeah, all that free food we get over there is just bad for the stomach.
I don't know. These are awful good.
Thank you for doing this.
No problem. It's the least I can do.
What's the most you do?
I don't know.
Roger,
Yeah,
at the office, we have Office 365 on those, or the new,
yeah, well,
because they have automatic save on them. And that may be what the problem is.
Yeah, Office 365 will do a save automatically to the OneDrive. If you don't want it, do it.
you gotta turn it off.
You gotta turn it on.
And maybe that's what some of the problems we've been having.
That and Adobe came out with an update. Didn't tell anybody about it and it creates a shadow on there. So the next time you bring it up, it's all crap.
That's-
But as soon as you type in, it all disappears. I don't know.
But then it ends up printing out the wrong one.
I can tell that.
Well, that's what was happening the other day.
It stays for the print.
It would come up on the screen correctly,
Yeah.
you say print, and it would go back and print the other one.
Too good.
Okay, no. We had to end up filling out page one by hand.
Yeah.
And so I think about it last night when I was working on something else. And the damn thing was auto saving on me. I didn't have it turned off.
So you had the same problem at home?
Yeah, but at home it's different, you know. I didn't have the printing the wrong one out. But it was saving everything that I was doing. I didn't know it was saving it. I don't know that much about it. How?
We've been working with Dell to try to straighten out the little range base problem.
Mhm.
And next Thursday, we're gonna meet, we got a plan upgrade on the, Dell hardware. That one of the stations that went out, he's supposed to come in with a technician and fix it. Interesting.
That's SARNet. It's a network of repeaters, most in Florida, into Georgia, are all interconnected. And there's a repeater over in Cocoa as part of that, which is what this one's on.
This is K1 CPO. Anybody in the room? No.
That's a,
Yeah.
the cable you have on that.
Good ask. Good morning, Dave.
Yeah,
You're
I
here
just didn't
at,
take it off.
Clover.
What?
That's Dave's repeater.
Oh. Dave, this is Bob.
That's down at Courtney Springs where that. That's where that
On
repeater,
one of their buildings,
up on the 13th floor.
yeah.
Did he say he was working?
He's working, yeah, that's why may not be able to answer right away.
Go ahead.
He said, go ahead.
Yeah, this is Whiskey 3 Romeo Delta Lima. Are you free at a moment?
At the moment. Like,
We're doing good. We finished first section about on time. So far, they got most of the questions right. Yeah.
I imagine most have things.
That is number 10.
Okay, I'm gonna let them chat with you a bit, see if they got any questions for you. Dave is our kind of repeater expert in
One of them, yeah.
I don't know, I'm trying to think of something to ask him. Where's he located?
She's at Courtney Springs,
I don't even.
right down by the airport here.
Oh, okay.
Is he one of the inmates over?
I'm sorry,
Is he a resident?
no, he works there.
he works there.
Yeah.
No,
Well,
I don't know. What do I ask that guy?
You got a question about amateur radio? He'll have an answer. Or UFOs. He's big on UFOs.
oh, yeah.
This is student Steve, wondering if you have an opinion on amateur radios handheld for new guys.
Welcome to Ham Radio. Yeah, I would go with the budget session to begin with. It's definitely make sure you find something that's rated, and approved. And then you can turn line right down, Southend 9R, and I got a organization. IRL.
Somebody else come on.
$1,000.